started. Let me know. No questions? All right. Okay. All right. So last time we talked about the KDB equation. We, by example, introduced this method of essentially just converting the PDE to a pair of second order nonlinear ODEs, and then we turn that into, a pair of first order nonlinear ODEs. And then we did phase plane analysis on that, and sort of sketched essentially the phase plane motivated by an equilibrium analysis. We're going to do some related things today with the Fisher equation and the bistable equation, which are both kind of canonical models of nonlinear waves as well. So let's start with Fisher's equation. So the idea with Fisher's equation is that it's supposed to model a combination of logistic population growth, okay, with diffusion, okay? And so this is like animals that roam and reproduce. Okay, so I live out in Louisville. I look out my window. I see lots of rabbits hopping around. Rabbits famously reproduce very rapidly. They move around by diffusion, right? And so if you have a patch of rabbits locally, they're going to reproduce. They're going to have babies. Then they're going to spread out, okay, and spread their population around. So just the logistic equation would look like this. It would just be du dt is equal to alpha u max minus u. Okay, so we can get some insight into, before I write down Fisher's equation, what's going to happen at just a local point in space. Essentially, there's two equilibria, right? So one of these is u equals 0, and the other is u max, right? So u equals 0 and u max, okay? Their stability is given by linearizing, right, around this right-hand side, okay? So if f of u is equal to alpha u, u max minus u, f prime of u is equal to alpha u max minus u minus alpha u, there we go, okay. So that's going to be equal to alpha u max minus 2u. Okay. All right. So the stability of our fixed points then is f prime of 0 is equal to alpha u max, and f prime of u max is equal to minus alpha of u max, okay? And so that makes this point unstable, and that makes this point stable. And so the idea is that over time, right, if I'm looking at u as a function of t, if I start out with some organisms here, they're going to increase their population until they get to u max, okay? why don't they just keep reproducing forever? Well, that's the whole point of the logistic equation, is that you have some resource bound. And so essentially, when U gets above U max, the rabbits run out of food, they start starving, okay, until the reproduction rate sort of balances out the death rate. Okay, so this is as opposed to just pure exponential growth, right? So this is your typical situation, but if, obviously if you start out at U0 equals 0, you would just not ever leave U equals 0 there, okay? So why do I bring this up? Why do we do this starting simple analysis? Well, it's because the fact that U equals 0 is an unstable equilibrium and U equals U max is a stable equilibrium, it creates some interesting properties of the traveling wave that are going to be different than when we look at the bistable equation. The bistable equation actually has two stable fixed points separated by an unstable fixed point. Here, if we just sort of draw the phase line, right, we have this is U equals 0, and then this is U max here, right? And if this is just U, everything should flow into U max in this case. So sometimes these fronts are called pushed fronts because essentially the unstable equilibrium sort of pushes the state variable away from it. Okay, so that's what I'll say about the logistic equation. Now that we have that in mind, let's introduce the Fisher's equation. So Fisher's equation is what? Well, it's just du dt is equal to some diffusion coefficient that I'll call d times Laplacian of u, so it could be in Rn, plus alpha u max minus u. And this is really, part of a general class of what are called reaction diffusion equations, okay? You have some reaction term. Here it's just reproduction, and then we have a diffusion term here, okay? Viscous Burgers was this way too, right? The nonlinear wave propagation term in Viscous Burgers, right, is your reaction term and then diffusion term. Okay. So what are our parameters, right? Well, they need to be physical. So D is greater than 0, alpha is greater than 0. This is like your growth rate. This is your diffusion rate, and then, or coefficient. And U max is basically the max population level, okay, per unit space, okay. So for instance, right, in R2, we could have U equals U of x, y, t, and Laplacian would equal dx squared plus dy squared, okay. Let's stick to 1D analysis for now, okay. And so in this case, x is in R, u is equal to u of xt, and Laplacian is just equal to dx squared, okay? Because we can actually do things in that case. And you can think of this as a model of, right, let's say you have a big herd or a group of animals here. This could be a shoal of fish, or I don't know, something with a quick reproductive turnaround, right? Their population is going to invade in that direction as they reproduce, right? If you have a big population of them. Okay, so it's an approximation. You could also think of a 2D population that has, you know, a fairly straight boundary of its edge right there. So given this picture that I've drawn, right, you can see that once this population starts to reproduce, because they can't just keep growing in this area, they need to invade other territory in order to have resources to eat. Okay, so that's the idea. Now, you know, this model models other things like, you know, chemical reaction dynamics, but I don't know. I think the population growth is a little more intuitive, so that's sort of how I'll talk through this. Okay, and
Um,
go ahead.
so I think the way you said that is that as it grows, it also grows into that area. But does it, just looking at the equation, it looks like it also diffuses. So like on the boundary, it should go down, or like at that border, it should go down as it
Right.
diffuses into.
So even if you didn't have reproduction in this case, right, you would get diffusion, right? But once you hit some upper limit here, reproduction is not going to help you anymore. So yeah, I'm sort of, you know, coupling together the two effects lead to this propagation of organisms. Yeah. So, but yeah, you're right. So to make that point, right, essentially what we have here is Fick's law sort of governs the diffusion. What is Fick's law? It's just this sort of population flux law. And the idea is that the population is going to seek to move down gradients. So minus d gradient of u is going to be the uh, the 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 physical law that this substance, which is our population, is going to follow. And this thing here, right, is our reaction term, which is going to be logistic growth in this case. Okay. So the population moves down gradient. Okay. So wherever there's not organisms, the organisms want to move there. Okay. Because, you know, they're motivated to get more food there, etc. Okay. All right. So sort of setting everything up, right? If we look in 1D, okay, and we also, for now, just to get all of these things out of the way, we set our diffusion, our growth rate, and our maximal population just to 1, okay? If you take asymptotics, we'll talk about a process called non-dimensionalization, which essentially allows you to eliminate parameters by rescaling your variables. So for instance, if I rescale time and I rescale space in units that correspond to my parameters, I can often absorb these parameters into new variables, okay? But just for simplicity here, we'll just set them to be equal to 1, okay? And, right, we have u is equal to uxt. And so then my effective PD is just uxx plus u1 minus u. Okay. All right. So nice, handy PDE to analyze now. If I suspect that there's traveling waves, what do I do next?
You plug in a Fourier mode. It's a nonsense.
That's one possibility, but that will only work in the case of a linear equation. So what's the ansatz I make for nonlinear equations?